So when you have a radioactive substance and it's gone through an alpha decay and then it's gone through an alpha decay again, if I told you it went through 2, then basically you're just checking your math. It's 239, your bottom number's a 92, that's uranium. And I know it's uranium just because I know that one on the periodic table, but it's still radioactive, okay? When you do beta decay, and you may think, well, I am not quite through that video, that's fine, make sure you watch it here in a minute, but beta decay looks like this, okay? 0, -1 beta, okay, so it's just got the beta letter, okay, so I do the same math. Notice here, 243 plus 4 is 247, so what number plus 0 gives me 14? That's easy math. What number plus a -1 gives me 6? That's a 7, right? And so in that case, nitrogen is element number 7. So you look at alpha decay, you look at beta decay, you even look at neutron decay. Cool. Now here's the thing. A couple things for you. First thing I'm going to tell you is nothing does just all alpha decay. If you were to look at the periodic table in an alpha decay, what's literally happening here is when I had curium and it went through alpha decay, it dropped 2. If it went through alpha decay again, it would drop 2. Is that still radioactive? Yes. If it did an alpha decay, it dropped 2. Is that still radioactive? Yes. It would drop to 88, and then it would drop to 86, and then it would drop to 84. Is that still radioactive? Yeah. And then it would drop to 82. Is that radioactive? No. So eventually all uranium could end up as lead, but it would take a very, very, very long time for it to happen. That's why in the area of Chernobyl, where that nuclear power plant went off, every single atom would have to go through all those steps, naturally. They say it'll be radioactive for 25 million years. In a beta decay, it's sort of weird. In a beta decay, it actually goes up a spot. So here's what I'm going to tell you. Most things don't do just alpha decay or beta decay. What actually happens is they will go through a pattern. It may be 2 alpha decay, 1 beta decay, and then 1 more alpha decay. And so all you do is just do the math. It's pretty simple. Okay? 4-2 helium twice, going up once, and so you're just showing what's going on. Okay? Now, that's not too hard. I've done that in most of the video. But what I really want to do is I want to tell you, how do we have that? Okay? And the reason I say that is because if you look at curium in the periodic table, it's a ghost letter. It's made in the laboratory. So I'm going to teach you how this happens because I hadn't made this in video, so I'm just going to show you real quick. Okay? If I were to take a golf ball and I were to throw it at a glass window, you would expect it to go through. It's going to shatter the glass, right? Okay? But what would happen if I took a golf ball and I threw it as hard as I could at glass and it stuck to it without breaking the glass, but it stuck to it? First of all, you're probably going to walk off and say, I didn't see that, right? That's weird. That shouldn't happen, right? Okay? And in essence, that's sort of what happens when they made the elements. And here's why. Every time you have an alpha decay, you not only have an alpha decay, you have a little bit of gamma. Okay? And gamma is just energy. Okay? So when an alpha particle flies off, you have a little energy given off. Not even enough to really detect. Okay? With a beta decay, you have the same thing. A little bit of energy that's given off. But when you put it on the end of a bomb and you drop it and it hits the ground, boom, you make trillions upon trillions upon trillions upon trillions of atoms all break at one time. That little bit of gamma becomes a big amount of energy, and that's why when the bomb hit Hiroshima and Nagasaki, there was such major devastation. For a half second, it was the temperature of the sun, and people were literally cremated instantly, okay? Because it's so much energy. Now, that's on the bad side. But what we've learned is, we're probably going to run out of wood, oil, coal, natural resources. What if we could tap into the energy inside of an atom? What if we could cause radioactivity to happen under controlled situations, catch that energy, and make electricity? And that's why they started making these elements. Let me show you. The largest naturally occurring element on the periodic table is uranium, 238.92. And what they did is they bombard. Now that's a weird word. Bombard is really simple. If you've ever done paint guns, okay, or Nerf war, or anything like that, and you have 2 or 3 people gang up on you, that's what bombarding is. You're just doing this kind of thing because they're trying to kill you, right? Okay, I did that with my youth group one time. All of a sudden, they all turned on me, okay? I didn't have a chance, okay? So what they do is they'll take uranium-238-92 and they're going to bombard it with something, okay? So let's just bombard it with, let's just say something like helium, okay? So what they're going to do is they're going to shoot a bunch of helium atoms at this. Now, what happens most time is when they hit that really big atom, everything just breaks into a bunch of pieces. But what they found was sometimes the helium would stick. And when it would stick, something weird happened. Because if this stuck to this, simple math, 238 and 4 is 242, 92 and 2 is 94. When it stuck, you made actually, if uranium is the largest element on the periodic table, and you shot something at it, it stuck, you made a new element. Why? It has a different number of protons. And with that different number of protons, it now has 94. Now, 94 on the periodic table is now called plutonium. So any of them that are ghost letters, somebody made them in a lab. Now, you have to understand this. Somebody didn't get up in the morning and go, I'm so bored today. I'm going to make an element. Okay, it didn't work out like that. Okay? But in doing the testing, why? It was all about having a new form of energy. Okay? And so they made a plutonium. And so they wrote up their findings, and another lab had to prove, yeah, we did that too. And so whoever did it got to name it, and they named after the planet Pluto. It's called plutonium. Now, what do you think happens when you shoot bigger things at it? So let's say you shoot a nitrogen. That's not where that N goes. 14.7 nitrogen. Okay? Most times when it's going to hit, imagine, anybody ever played with paint guns? Okay? No, not very many people. Okay, so I'll just tell you this. You've done this before, friend. You ever had somebody shoot at you and it didn't break? It feels like they hit you with a rock. I mean, it hits you because it's supposed to explode. When it hits you and bounces off, it's like, it hurts. I mean, those are the ones that really bruise because they don't break, okay? And so what's going to happen most times is when these hit each other, they just break up and into a bunch of pieces. But if this sticks to this, quick math, the bottom number is going to be what? 99, right? Okay, and the top number, you're going to have to do a little bit of math, so that's going to be 252. And we now know that element is 99 is ES, which is Einsteinium. Now, so let's take the example I said a while ago. Take a golf ball and I throw it at glass, it should break it, right? Okay, that's way bigger than helium, right? So if I take a baseball and throw it at glass, it should go through. If I throw a baseball at a window and it sticks to it without breaking it, that's even more freakish, right? That should not happen. So do you think this happens very often? No, it doesn't. Now, what really happens is when you have something like this, and you shoot something like calcium. Calcium's element number 20. Your top number, your bottom number is 112. Okay? And your top number, add 40 to that. Quick math, thank you. 270, 112. Woo! 112. Well, on my periodic table, it's called that, meaning some lab has actually made it, but nobody, as the time we bought that periodic table, had proved it and done it in their lab. So they hadn't given it a name. Some of the newest periodic tables now have that name. So let me say it like this. That's huge compared to a helium, right? So imagine I shoot a cannonball at a glass, at a window, and it doesn't break it. The bigger the thing you shoot, do you think it's easier to stick? Why would they do this? As they're going along, they're hoping that eventually they're going to make some kind of new element that doesn't make a big atom. Here's what they're looking for. All the gamma that comes off, all the energy that comes off. Can we make a new source of energy for the world? Okay? This is what is called, you'll see in one of the other videos, these were all called fusions. What does it mean when something fuses? Yeah, it sticks to it. When something fuses to something else, it's stuck to it, okay? And so when it's fused together, okay, when it's fused together, you made something new, but you get lots of gamma. Very simply, what they're doing is this. You take a nuclear power plant. I'll have to call you right back. It's always during a video, okay? And so what they do is they take a nuclear power plant, and here's what they do. You take uranium bars and you put in the middle of that nuclear power plant, and you have 10-foot walls, 10-foot concrete walls. And then you have a layer of water, and the 10-foot wall of concrete, and a layer of water, and a 10-foot wall of concrete. I am not the best artist in the world. Let's say that's uranium. You shoot a neutron into there, you break it all open, what do you give? Lots of gamma. It gets, whoa, really hot. When it gets really hot in here, what does it do to the wall? The wall gets hot. The wall is now touching water. What does water do when it gets hot? It heats, it evaporates, it boils. And when it boils, you have steam. And when you have steam, what they're going to have is they're going to have pipes that run out the side over here, and they're going to move a turbine. Now, have you seen on the top of a house when the wind is blowing the turbines that are pulling the heat out of somebody's attic? Okay, you know what I'm talking about? Lets the heat out of your attic. Imagine huge turbines that when you're shooting all this steam by it, you're making electricity with all that heat. And so what they do is they just pump the new water in there, cool it off, cool it off, cool it off, cool it off until it stops getting heated up. And then they start the reaction again. All the water heats up steam, more and more and more and more and more electricity until it slows down. Then they start it. As long as this is controlled, you have an endless supply of energy. In Chernobyl, what happened was they started this and their pumping system broke. All 3 sets. So the temperature in here gets higher and higher and higher, and you have what is called nuclear meltdown. It gets so hot that these rods go right through that 10-foot wall of concrete like a hot knife through butter. It goes straight through it. And so basically this thing right here starts heading toward the center of the earth. When it touches if it touches floor, it'd melt right through it. If it touches ground, it goes right through it. It's headed toward the center of the earth until you can get it cooled off. So what happens when you have pressure in a small container? Okay, you take an old canister and you shoot a BB at it or whatever. That's a grenade, right? Boom, it blows up and it shoots nuclear waste all into the air. And that's what happened. It got out of control. So we're looking for things, we're trying to make these new elements so we get more and more gamma. What's gamma? Energy. Why? To make electricity, to have a new energy source. And so all of the elements that you see on the periodic table are ghost letters, have been made in the laboratory just for the fact of trying to find a new energy source. Does that make sense?